Last week we looked at how we could use the open and closed circuit tests on a real transformer to provide some performance data that will allow us to actually create the model for that transformer and model its actual performance. Now, had we been in college, we'd have that transformer by the side of us and we'd actually be able to do this practical work and see what happens. But what we're going to do is use historical data to at least go through that process, and you'll see that what I say is as correct as can be shown when we can't actually do the practical work. Okay, but it's like on some real data rather than just something made up from a book. Okay, so when we do this analysis, we said we're going to analyze the transformer for a resistive load of 546 ohms, which is one of the resistors on the board, using a primary voltage of 400 volts. So this is a step down transformer from 400 volts, I think, to 250, something like that. Okay, so that's what we're going to have a look at. So the first thing to do would be to do the open circuit test, which would involve us measuring the power in the primary side using a wattmeter, measuring the current and the primary voltage with an ammeter and a voltmeter, and measuring the open circuit secondary voltage with another voltmeter. And in previous times when that experiment work has been done, we had the following readings: power 3.6 watts, the primary voltage, which was set to 400 volts, which is the nominal primary voltage of the transformer. The current flowing measured in that primary circuit was 19 milliamps, and the secondary voltage open circuit was 251 volts. So that's your
19 or 14 milliamps?
19.
19. Yep.
Hang on, I'll write them a bit bigger over here. 2.6 watts, 400 volts, 19 milliamps, and 251 volts. Yep.
Yeah.
Now, have your handouts on that page got the formulas or not, or is it like my page, just with the table?
Yeah, just like yours.
Okay. So what we've got to do now is use those values to find the various pieces of data that will allow us to find the value of the two parallel components, RC and XM, in the transformer. Yeah.
Yep.
Okay. So what do we need to do first, do you think? What data can we find from the information that we've got from the open circuit test? First of all, can we find A? The transformer ratio?
Yes, you do the primary voltage divided by the primary voltage
Yeah.
squared divided by the secondary voltage.
Don't need to square it.
Oh.
I is equal to, you get it either from N1 over N2 or V1 over V2 or I2 over I1, remember. Any one of them will give you the transformer ratio. So in this case, we can do I is equal to V1 over V2. That is 400 over 251 equals whatever it is.
.59.
1.59, let's say 1.6 then, shall we, among friends? Yeah. So that's the first piece of data that we've found, is that I is 1.6. Yeah, we're going to need that later. All right.
Yep.
From the information found, what else can we find? What will the current and the voltage help us to find?
A power.
One of the powers, yes.
One of the powers. Yeah.
Wouldn't it be there? Is it the phase power? Is it? It said
The
P.
what power?
It said P phase power. I got that wrong.
The measured power in watts is 2.6. Yeah. But what other power can we get? We calculate from knowing what the current is, which is 19 milliamps, and the voltage applied, which is 400. Remember our triangle. There's P. We know that. We measured it. It's 19 watts. But a power triangle also includes Q and S. And it includes a phase angle as well.
We can work out S by doing I times I times hang on, I times EP.
Yeah, well done. So S, the apparent power, S is EP times IP. That is 400 times 19 times 10 to the minus 3, because that's milliamps, equals what we got.
A 7.6.
7.6.
Yeah.
What are the units of apparent power?
VA.
VA.
VA. Yeah, VA. Okay. So now we know S. Now what can we find?
We can work out Q.
Yeah. Q is equal to
Square root of S squared minus P squared.
Correct. Equals root 7.6 squared minus 19 squared. Oh, hang on. Hang on. How come it's not 19 watts? Is it? 19 milliamps is 2.6 watts. So this in here, and the other watts can't be bigger than the power can't be big, can never be bigger than the apparent power, can it?
No.
And the answer to that is
7.14.
7.14
Yeah.
units.
VAR.
VAR, volt amps reactive, yeah. Okay, not video assistant referee. So now that we've got that data, how might we find the values of RC, the parallel resistor, we got think about finding it in terms of the powers. What formulas for power have we got? Remember how these components are connected? Just go on another page and draw a diagram. We've got our generator here, yeah, feeding into this transformer. So we've got 400 volts. And we're looking to find the values of two parallel components, one there and one there. And then that feeds off into this open circuit transformer. I equals 1.6. Yeah. So we want to find the value, resistive value of R and the value of the inductor, at least the XM value. Yeah. So how can we do that? We know this current. We know we've got 19 milliamps here. Yeah, but that's no help because it won't be 19 milliamps in each of these legs here. So we can't use the current. But we've got voltage, we've got power, and we've got reactive power. So how could we use them to find this RC and XM? What are our three different formulae for power? Basic formula for power.
I squared R. That's one of them.
I squared R. No good because we ain't got the current, but that is one of them. Yeah. Second one.
E squared over P.
Yeah, so the basic is V squared over. P is V squared over R. Yeah. And the last one is P as I times V. Yeah. But this one and this one are no good because we don't know the current. So we're going to use power is equal to the voltage squared divided by the resistance, rearranged to find the resistance. And we also know that Q is equal to V squared over X. So we can rearrange that one to find the value of XM. So you can go RC is equal to V squared, or E, we've been using E, haven't we?
Yeah.
EP squared over P. And this one is EP squared over Q. Yeah? What you got to do with this kind of problem is look at the information you've got and then think about what formula you can use to find another piece of information to gradually break the problem down. Yeah. So we got 400 squared over 19. Yeah. And 400 squared over 7.6. And what results do you get from them?
Where's the 19 from, Mike?
No, hang on, 19's wrong. I've done it again, haven't I? 19 milliamps is the current. It's 2.6, Warren.
Right.
2.6 watts.
Mm-hmm.
I've got 19 on the brain.
That's a big number.
So what do we get for RC?
.5 times by 10 to the 3.
Yeah, so that's 61.5 kiloohms, yeah?
Yeah. It's quite a lot. RC.
And the XM?
$21.1.
21.1. Ain't what I got. Hang on, no, hang on. I got 7.1 var. I have 7.14. Oh, I'm looking at, yes.
Yeah,
so
that's the Q.
7.14.
I've got 22.4 times a 10 to the 3.
Yeah, 22.4. Yep.
The ohms as well.
All right.
Yeah.
You all got what you want from that?
Yep.
Yeah. So these two components values we got, RC is equal to 61.5K and XM is 22.4K. Yep. So if we can, what we do is if we find the separate currents through each of those, so we find IR we'll call it IC because that's called RC. IRC, yeah. How can we find that? Ohm's law. You ought to know that by now, boys.
VR.
VR. I is equal to V or EP over R, isn't it?
Yeah.
Yeah. It's 400 divided by 61.5 times 10 to the 3 equals. I haven't got my calculator here, so I'll just go and get it because I've never done this one before. Just going to try and confirm that 19 milliamps is more or less right.
All right.
So 400 over 61.5 times 10 to the 3 is 6.5 milliamps.
Yeah.
And the angle for that would be for a resistor. Current would be 0 degrees, wouldn't it? Because the angle of a resistor is 0. Yeah.
Mm-hmm.
And IM is E phase over XM, which is 400 over 22.4 times 10 to the 3 angle. The angle for an inductor?
90 degrees.
90 degrees. Yeah.
Yeah.
So that's going to be
17.8 milliamps.
17.9 if you round it correctly, Warren.
Yeah, okay.
Because the 5 will take it up to 9, yeah?
All right.
17.9 milliamps. Angle
90.
minus 90. Yeah?
Yeah.
So now what we need to do is convert both to rectangular form. And add. So that's going to be, they're both milliamps. Yeah, so we can, that's 6.5 plus 0J. And then this is going to be 0 minus 17.9 J. Yeah, because they're both per components. So the resistor's only got a real part. The inductor's only got an imaginary part. On a phasor diagram, they're like this. Inductive current down there. Resistive current there. Yeah. And the resultant actual current being that one in there. Okay, you're happy with that? So we want to convert, we've got 6.5 minus 17.9 J. Convert that back to polar. my calculator's in damn radians. Shift, polar, 6.5. Shift, comma, 17.9 equals 19.04 milliamps.
Yep.
Angle 70 degrees, minus 70 degrees.
Yep.
Okay. So
That's
we
what
didn't, when we measured it, we didn't measure the angle. Yeah. But you can't, because they have an angle, you can't add those two quantities together in terms of Kirchhoff's current law without taking into account the angles. Because if we add two magnitudes, 17.9 and 6.5, we definitely don't get 19.04 milliamps. Yeah.
Right.
So that model has indicated the right current. Yeah. Okay. So you're both happy with that, yeah?
Yep.
Good. All right, but you've got to get this Ohm's law and its power formulas off the pat, because you're going to need to use them all the time in the exam. Need to get the right ones. All right.
Yep.
So, having looked at the open circuit situation, let's now have a look at the extra information we can get from the short circuit test and see if that will help us to develop a model that will allow us to indicate how this transformer will act on load. Yeah. Okay. So for the short circuit test on the next page, the data that you want is primary voltage. Remember, we would have to use a much smaller voltage so we didn't overcurrent the transformer. 40 volts was used. Yeah. IP was 246 milliamps. And the power was 7 watts. Yeah. The other data that we need from the previous bit was that A is equal to 1.6, wasn't it? Pretty sure that's right. Yeah, 1.6. Yeah. All right. Both all right with that?
Yep.
Yeah.
Yeah, 1 second, just writing it all down.
Okay.
Okay. Yeah, I've got it.
Okay, so using that we're going to try and use that data to build a model like this one on the next page. I'm going to go back a page in a minute, and I'm going to put a new page in. So what we've got to do now is use the data that we've just I've just given you to find values for R and X. Yeah. And then from that, we can put them on this model and use it to do these predictions for the real transformer. All right. And before we do that, I'll go to the last page, and we'll just fill in before we do the analysis, so you know I'm not cheating, what the final measured values were on the real transformer. Yeah. Oh, hang on. Yeah, I'll do that. So this one in milliamps was 274. Secondary current 426 milliamps. Secondary voltage 231 volts. And the power output 96 watts. They're the measured values from the real transformer. What we'll do now is build our model, calculate our values, and see how close we get to those actual values. Yep. You got that?
Almost. Second.
Just writing down the last two.
Good.
Yeah, I'm good.
Yeah, okay.
Right. Right. So from the information from the short circuit test and the value of A, how can we find these values? So we know, just draw the diagram, we're applying 400 volts to the transformer. We've got to find this R and X from the information that we measured, so that we can use this model. Yep. Any ideas as to how we can start that?
Do you have to add up the impedances?
Yeah. So what you're saying is, well, if we knew what they were, we could add them up. Yeah. But given the information that we've got, so we've got EP is 400. Yeah. Sorry, 40.
40.
Yes. So we got 40 volts from our data. Yeah. I'm going to take that away for a minute. So at the moment, on our open circuit test, yeah, we got 40 volts for the primary. Primary current was 246 milliamps, and power 7 watts. So what can we find using that data? You mentioned ZP, the total impedance.
Yeah.
I think that diagram I put up there, there's a bit confusion at the moment. I'm going to get rid of that. You know what we're trying to find? We're trying to find those two R and X values, but we're using the data from a short circuit test that we've been given. So if I know from what I've got over here, can I find the impedance, the total impedance of the primary side when the secondary short circuited? The impedance seen by the generator.
Is it 40 divided by 246 milliamps.
Yeah, yeah. Z, yeah, primary is EP over IP. Yeah, that is 40 over 246 times 10 to the minus 3.
And that is 162.6 ohms.
Yeah, so let's go 163, shall we?
Yeah.
Yep, 3 significant figures. All right. So that's the total impedance. Yeah.
Yep.
Now, given the information that you've got, is there a way that we can find the value of the resistor?
Is it power divided by current squared?
Current squared. Yeah, we're going to use the IP squared over power is equal to IP squared over times R. Yeah.
Yep.
So we've got to, therefore, R in the primary is equal to power over IP squared, which is 7 over 0.246 squared.
And I got 116 ohms.
Yeah. Okay. Now we've got that new piece of information. What else can we find?
We find X, I guess, can't we?
Yeah, because we've got
Total.
2 sides of the impedance triangle, haven't we? We've got Z and we've got R. So now we can find X. Yeah. XP is root ZP squared minus RP squared. Yeah. Root 163 squared minus 116 squared equals 115 for XP. All right, so that's what we're going to do. So I'll start a new page, EG Here's our transformer terminals. We want to model up with 400 volts there. We got an R value that was 116, an X value that was 115, secondary terminal there, and a load there that is Z2 dash, yeah, and this is E2 dash. Okay. Yeah.
Yeah.
So, where are we going to start? One other thing we know, the actual Z2 is 500. And 46 ohms.
Ah, right. Okay.
So where did you get that from? 546 ohms.
Because that's when we actually do the practical, Ben. That's the specified load.
Right, I see. Yeah.
So we would connect a 546 ohm resistance across the secondary terminals.
Right, I see.
Yeah.
Yeah, that's fine.
It's okay.
And then we were to work out ZL.
Well, we got ZL. ZL is this, the Z in the secondary.
Oh, sorry,
But
ZL.
we want to. We want Z2 dash, don't we?
Yeah.
Can you remember how we calculate that?
A squared times the Z2.
Yeah, well done. So that's 1.6 squared times 546 equals. You're back, Robbie.
Yeah, I'm having a bit of trouble with the old internet at the minute. I'm just moving to a different room, see if I can get some signal.
Okay. Right, what's this Z2 dash in, boys? What did that come out to? $1397. 1398 actually. Yep. And as that's a resistor, that'll be 0 degrees if we need it. Yep.
Yep.
Right, Warren? I lost Warren now. You got your microphone off, Warren.
Yep, there we go.
Right, here we
Okay
go.
with that?
Sample.
Yep. Okay. So where we're up to now, Robbie? Hang on a minute. It's just all right.
Yeah, I can't see what. Yeah, okay.
So we're going to find ZT, the total impedance. Yeah. So what we've got is RP plus Z2 dash, they're both resistive, yeah, plus XPJ, because that's inductive, ohms, yeah. So that's 116 plus 1398 plus, so those two are together, plus 115J ohms. That adds up to, I believe, 1513 plus 115J ohms. What will that help us find?
We can then find IP.
Yeah, probably best if we also get a polar version of that as well.
Okay. I've got 1519.4 ohms, angle at 4.34 degrees.
1519 ohms,
Yeah.
angle 4.34.
Yeah, degrees. Yeah.
Yep. So now we can find IP, because that is EP over ZT. 400 angle 0 over 1519 angle 4.34 equals
0.26 amps. Angle a minus.
Have we got a third significant figure for that, Warren?
Yeah. 3.
0.263 amps, angle
A minus
minus
at 4.34.
4.34 degrees. So you're looking at 263 milliamps magnitude. Yeah. Okay. So that's the primary current. Yeah. So secondary current. How can we find that? From knowing the primary current, IP, how can we find what would be I2 dash? What is I2 dash equal to? In terms of actual amps, that's equal to IP, isn't it? It's the same current in this loop circuit. But how do we get from I2 dash to I2? When we're transferring from the secondary, how do we get I2 dash? Remember?
Is that I2 over A? And then you rearrange?
Yeah. So that is I2 over A. Therefore, I2 equals A times I2 dash. Yeah. So that's 1.6 times, and we also know that IP is equal to I2 dash. So that's 1.6 times that current we just measured or calculated, 0.264, was it?
3.
0.263 angle minus 4.34 degrees equals.
Yeah, so I've got 0.421 and then the same angle.
Yeah, it will be the same angle, not amps, angle minus 4.34 degrees. Yeah. So that's our secondary current we can use for comparison. Yeah. Now, there's two ways that we could find the secondary voltage. Tell me one of them.
So if we've got the secondary impedance, you can do it that way, or use the...
Yeah, we've got the secondary impedance because all that is the load. Because remember that the secondary winding impedance is all built into that RP and XP anyway.
Yeah.
They're all built in, yeah. So the only load we got on the secondary voltage is the actual load resistor. Yeah. So one way to find E2 is to do E2 is equal to I2 times Z load. Yep. 4.421 amps angle minus 4.34 degrees times 546 equals.
Is that 546 you've got there?
Yeah, it is, yes, Robbie, yeah.
Okay, I got, well, if we round it up to 3 significant, then I've got 230.
230 volts, angle, minus 4.34. Yeah.
Mhm.
The other, and probably more tricky way, is that we could go down the E2 dash is equal to IP times ZL dash, which is 0.241 angle 4.34 minus degrees times 1397 equals 369 angle, and that's volts, that is, volts angle minus 4.34 degrees. Yeah. Therefore, E2 is equal to E2 dash over A, which is 369 angle minus 4.34 over 1.6. I think you should get the same, more or less the same result.
Yeah, pretty much. 231.
Yeah.
So 3 significant figures.
Yeah. Okay. So that's the secondary voltage and the secondary current. Okay. Now, because the load is fairly resistive, we can just use the magnitudes of the current and the voltage to find the power. So
Sorry, can
power.
you, I didn't finish writing.
Hang on, Ben. Yeah.
That's fine.
Way you go.
Oh, thank you. Actually, I'll just take a photo of it. That'll be. Yeah, that's fine. You can carry on if you want.
Carry on, yeah?
Yeah.
Right. Power is equal to I2 times E2. Yeah, is 0.421, was it? The current in the secondary we got?
Yeah.
Times, and we measured and we calculated 230 volts, didn't we? $97.
Yeah, pretty much.
97.1 if we stick to our 3 significant figures. Yeah. So comparing those results, so 97.1 we calculated for wattage against 96 watts measured. Secondary voltage we calculated 230 against the measured 231. What was the secondary current we calculated?
421
421 milliamps. So we're about 5 milliamps out. Not much in 400, is it? And the primary current we calculated was
263.
263. Yep. So, you know, that model's pretty close. Yeah. If you go to 2 significant figures, which is quite often as much as you can measure accurately, that's pretty much spot on, isn't it? Yeah. One other thing to note is the difference in phase angle. On load, we got a phase angle of 4.34 degrees. Yeah. When we were offload, that angle was 70 degrees. Yeah. The power factor when it's on load is pretty good. You only got an angle in that impedance triangle of 4.34 degrees. It's not wasting too much. It's not causing too much problem with power factor, this transformer. Okay? You're all happy with that?
Yeah, sorry, I need to go to slide 10, please, Mike.
10, yeah, I can, yeah. There you go.